are reactants in that case. Why would we not favor the formation of the products? What type of reaction is that? What type of mechanism are we showing? SN2. Okay, could we have shown it as an SN1? No, why not? No breaking of our octet. We have a strong nucleophile. Strong nucleophile suggests the bimolecular mechanism, our SN2. Okay. So we can't do our SN1, so we got to be running that SN2. What's the issue with that as an SN2 reaction, Sean? Sorry, you want to finish chewing?
Tertiary.
We have a tertiary substrate. What are the odds we're going to do a backside attack on a tertiary substrate? Not going to happen. Okay? That last step of the mechanism is not likely to occur because of the SN2. Okay? What does that suggest then about our ability to make the acetal under a basic environment? It's not going to happen. Okay? We can't actually form the acetal under the basic environment. We end up stalling out at the hemiacetal, which is undoubtedly what your book was presenting, but you have to understand the reasons why. Okay? The reason why is we can't continue that next step. Okay? You all saw the video on our acetals? In theory. So we've got the acetal mechanism. So we could have gone through and made the electrophile more electrophilic by adding an acid. The acid protonates right at the very beginning. Okay. Getting us the resonance stabilized carbonyl compound, okay, which ends up showing or placing a formal charge on the carbon of our carbonyl. We now have a much more active electrophile that can react with a weaker nucleophile that we can carry through the rest of the mechanism. We end up doing the same steps, except that under the acid conditions, we'll end up protonating and deprotonating a couple more times. So instead of having 3 steps, we've got 1, 2, 3, 4, 5, 6, 7 steps. Okay? So why do we have to do those extra protonations?
Make OH a good leaving group.
We have to make OH a good leaving group, right, which is happening in, where is it? Second row, this kind of system. Okay, we've made it a good leaving group, and now it leaves here. So we could call this the activation of our OH, kind of like what we did when we used H2SO4 or PBr3 or I'm going to start using the easy ones, PCl3 or fair enough, HCl could have worked, but we're going to say no. There's at least one more big one. I can think of actually 2 more. PI3, not a bad guess, but no, that's...
Go down the Halens. SCH2, wait, say SCH32.
It's going to be a bit unfair to play hangman in this case, because some of those are numbers.
1, 2.
2. And
1.
whoa, I don't even know what that letter was supposed to be. Ortosyl chloride. Okay. This goes back to unit number 1. What are we doing, or what did we do in that section? Our useful substitutions. We converted the alcohol into a different functional group so that it could leave the structure. What are we doing here? The exact same thing. We're setting it up so that it can leave the structure, okay, by turning it into a good leaving group. Same general concept as what happened in all of those. We can't use all of those as reagents for this, so don't start making that leap. These are just examples relevant to making the alcohol a better leaving group. Okay? So we did that protonation. Why did we not, say, deprotonate this alcohol first? If I deprotonate it, wouldn't it become a better nucleophile so it can react faster? In fact, actually, I circled the wrong one. Let me clear everything. Why did I not deprotonate this alcohol first? If that species is deprotonated, I have a strong base in an acidic environment. I'm not allowed to do that. So the nucleophile must attack first, right, which then sets me up with a strongly acidic structure with that positive charge. Okay? That is okay to form in an acidic environment. There's an excess of positive charge effectively floating around. Okay? So we have to be careful on when we protonate and deprotonate to match the conditions we're running under. The acidic one, or pretty much all of the acidic conditions that I'm aware of, are the most frustrating because you have lots of protons to take on and off. The big summary of all of this, which is what you're ultimately responsible for, and we'll look at here in just a second, is looking at converting between carbonyls and acetals, okay, when and how we make this conversion. To go from the carbonyl to the acetal, I need to add an alcohol, or sorry, a hemiacetal. To go from the hemiacetal to the acetal, what do I need to add? Another alcohol. What if I want to reverse the reaction? I need to add water. What happens to reverse the next step? What do I need to add? Interestingly enough, nothing. I'm not adding anything at that stage. Okay, the oxygen from our water is that one there. What if I wanted to take this to the hydrate? Okay. What happens when I react the hydrate? What am I reacting it with? Water and carbonyl. Where's the carbonyl? Right there at the top. React it with a second equivalent of water, and what do I end up with? There's my hydrate.
So you do need 2 waters to get all the way to the hydrate.
You would need 2 waters to get to the hydrate because the oxygens are the ones coming from water. Okay? So what we're trying to do is find those patterns and hook up those connections. This is a fair mechanism to put on the test. Not a bad idea to go through and study it and make sure you know how it works. Okay? There are also other mechanisms to put on, but this is a fair one as well. Okay? Questions? Okay. Questions about anything from the video?
Well, back to the beginning. We can't do this, the acetal can't be created in basic solution.
The acetal cannot be made in basic solution.
It has to be
Has to be under acidic conditions. Why?
the reactants are favored in the last step.
Well, why are the reactants favored?
Get that.
You're doing an SN2 on a tertiary.
You're doing an SN2 reaction on that last step to make our base. That last step is not likely to occur under basic conditions.
Well, we can start under basic conditions and then add acid, or is that?
Well, if you're going to start under basic conditions and add acid, all you're doing is neutralizing all the acid, going all the way back to the carbonyl, to then turn right back around and go the other direction.
Wasting a bunch of time in the product.
Yeah. You don't really waste product, you just dilute it. Okay. Mechanistically, it would really suck because then you backwards and forwards. Okay? Which then takes us to the next question here. Okay? Assuming you've answered your questions on acetals, what I now want you to go through and do is identify the following structures as either a hydrate, a hemiacetal, an acetal, or none of the above. Okay? And because for some reason it's switched like that, there's 2 more that we'll be looking at as soon as you finish those top 5. If you got questions, raise your hand. I'll come. We've got an acetal. We have the hydrate. We have an acetal. We have the hemiacetal. And we have none of the above. Okay. To be an acetal and a hemiacetal, you must identify a carbon. Okay, there's tons of carbon, so that's not super exciting. That is bound to 2 oxygens. Okay. That is a requirement with anything that associates with either the acetal, the hemiacetal, or the hydrate. So if we go through, we'll notice that we have that in 3 of those 4, however many of those, because I can't count, notice that they aren't all drawn in the same kind of pattern. If you take a look at the last one, I've got carbon out to 1 oxygen, but then I have a different carbon to a different oxygen. That doesn't match the pattern of the acetals. Okay? Within the other ones, sometimes you see the oxygens on the same side, sometimes you see them on opposite sides. Why would we shift it around? Because sigma bonds can freely rotate. We're showing a shift in the structure to make it less obvious, so you have to know what you're looking at. You have to have that spatial awareness that we learned back in first semester. Okay. With just the acetals, in fact, actually with all of these, I could go through and show the carbonyl. To get the carbonyl, what we end up doing is kicking off the oxygens and replacing them with an oxygen that comes from water. So I need to replace those oxygens with an oxygen from water. That means the other pieces then float off. They would be negatively charged, but then that's not an alcohol, number 1. And then number 2, those would be strong nucleophiles. And we know we can't form the acetal with strong nucleophiles. How do we make them weak nucleophiles? Add an H, we now have our alcohol. For the next one, that's a hydrate. I know I didn't tell you to do that one, but we can do the same idea. We're taking the carbon that has 2 oxygens bound to it. I want to make it the carbonyl. Well, put 2 bonds to an oxygen from that carbon. There it is. How about the next one? I may actually have to redraw this one. Same deal as we did with the hydrate. Find the carbon that has 2 oxygen bonds to it. Erase those oxygen bonds. And make them a carbonyl. But then we'd have nucleophilic oxygens. They're still attached to the structure. Okay? What makes this even more confusing is what if this question was on a test? How would that structure actually get drawn? 2, 3, 4, 5, 6, 7, 8, 9. I may have miscounted this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I think I got it. And then you'd be like, well, that doesn't look anything like what I started with. Yeah, because it cyclized. It looped back on itself. That's perfectly valid.
Why is your carbonyl like that?
Look at how that carbon's structured. We have 1, 2, 3, 4, 5, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7. Where is the carbonyl attached? Carbon A or 8. Okay. So it is easy to lose a carbon, particularly with the cyclic ones. Okay. And since I'm out of space, I'm not going to draw the hemiacetal one. Okay. So there were 2 more. Do you guys need time to try and go through and do another one? Or draw out the alcohol and the carbonyl of those 2? Or do you think you got it? Hold on a sec. Okay. We've got our basic skeleton drawn out. So what I would go through and do is erase, draw my carbonyl, there's my hydrogens. Okay. So the alcohol I'm using in this case is actually a diol, so I'm only taking 2 pieces as opposed to 3 pieces, okay, which will become relevant in a little bit. Okay. That last one, I attempted to do this, and who knows if I'm actually going to get it right, so let's give it a shot. And then 1, 2, 3, 4, 1, 2, 3. We would end up with that as our starting structure. The alcohol and the carbonyl are again self-contained. This one looks different from the one we had up previously because the carbonyl is actually in the backbone. 1, 2, 3, 4, 5, 6, 7 carbons. So again, this is a question where I would say drawing it out as a straight line is probably the wrong thing to do. Okay? Look at your structure, say, well, I want to erase those bonds, which then means I need my carbonyl. The oxygens need to turn into alcohols, and I have this structure that's all folded up on itself. Now that I have that acid, or my starting carbonyl and alcohol, I can backtrack that down to the structure that I've got drawn, which theoretically I did correctly. I've got 7 carbons, 1, 2, 3, 4 at position 4. I erased it, but that was my carbonyl. 5, 6, 7 carbons. At position 1 and position 7, I have an alcohol. Okay. How do you guys feel about it?
Good after we did that.
Okay. So it's a question of looking for those patterns and finding them. Remember, your structures can flip on top of each other. They can sandwich around. You can get all sorts of kind of weird stuff happening. Look for the basic pattern. Carbon with 2 oxygens bound to it. That is now a position that can have an acetal. Okay. And if you move into biochem, you can probably yell at me now if you happen to know the answer. That position is known as the anomeric carbon, okay, because it very particularly shows up in the acetals of carbohydrates. And carbohydrates have their own special nomenclature system, which is as good as it gets in biochemistry naming, and that system is still awful. Okay. But they can reference that position as your anomeric carbon. Okay. Questions about identifying your acetals or hemiacetals? Okay. So we've got 3 reactions shown here. Which side was favored? You should be able to answer this one because it was in the video. Top one, which side is favored?
Right.
Product. Next one. Reactant. Next one. Product. The question becomes why? Okay, in the top one, why would we expect the product to be favored? Okay. That is your very first step, and you should be making that statement. The arrow cleanly shows that we should be forming the product. Okay. But of course, that's going to be followed up with why. What do you got, Tyler?
Difference in sterics. So the reactant is not sterically hindered. So the carbonyl on the react side is not sterically hindered.
So you're comparing these two?
Yeah, but because you're adding the same ETOH to each one. So what's the difference between the two? The difference would be sterics. And
So we would expect that top one to go faster than the second one because of a steric argument. Absolutely. Okay. What else could we use?
Doesn't have to do with those hydrogens.
okay, hydrogen can't donate electrons.
Hydrogen can't donate electron density, which means the electrophile in the top one is more electrophilic than the later two. Okay? Stronger electrophile, that would suggest it should react to a greater extent. The last one, as Corey was bringing up, and he may regret, said 2 versus 3. Why is that relevant? No.
Entropy.
Entropy. Did anybody hear the story on entropy versus enthalpy? Why it's called entropy? The guy that discovered it or coined that term called it something so that it would legitimately be confused with enthalpy because it is that important. He didn't want people forgetting its importance. So he named it something close to the word enthalpy. Yeah, really nice. Okay. Entropy. Okay, the more disorder in a reaction, the more likely it would be favored. If we look at the 3 versus the 2, what would that suggest according to entropy? 2 is more stable. Not according to entropy. There's less disorder in our products, which would suggest entropy favors the reactant. Disorder increases as a function of time, period. So we would predict that our reactants should be favored, which this reaction goes counter to that. So there's 2 things competing here. Those 2 things are entropy and enthalpy, the reactivity of our electrophile, the energy stored there. Thermodynamics, in the top case, is the one winning out. Okay? In the second case, what happens? Right? It's now 3 to 2. It's the same system. Entropy favors our reactants. Okay? Do we have an equally active electrophile? No, if anything, it's less active. So what happens to thermodynamics? No longer helps out, entropy trumps, and we end up seeing our reactants favored over our products. Okay? So it is a careful balance between those. Last one. Since we talked about entropy, how many things do we start with? 2. How many things do we end with? 2. Is entropy going to be a factor? No. So entropy is out the window. We don't have to worry about it. Thank goodness. Okay. But now the question, what about the energetics? Okay. If we follow the same rules that we had in the second reaction, our energetics said that that's less likely to occur, which would suggest that in that third reaction, it shouldn't happen. And we do see it happening. Why? A lot of it has to do with that first step. Once we've formed that first bond, we have that reactive oxygen very close by. Okay? Which means it can swing in and kick out the water. And now say even that bond breaks, well, it can just as easily form because it can't float away into solution. You've got your reactive species tied to your structure, right? Which facilitates and allows that 5-membered ring to be more likely to form. What is special about our 5-membered rings?
Stable.
They are more stable. So that type of acetal is highly favored. We would predict that to happen. Okay. So if you find a 5 or 6-membered ring, those are expected. Questions about our acetals? Okay. The last one's particularly relevant. Okay. We can go through and convert that carbonyl over to the acetal. Well, why do I care? Carbonyl is reactive. Okay. It is susceptible to what? Other nucleophiles. So let's say I had a bromine on here and I wanted to, I don't know, chain lengthen by reacting this with another carbonyl. How do I get the carbon where the bromine is attached to that carbon? What can I do? What is the charge on the carbon in both those cases?
Slight positive.
Positive. Okay? Which means I have to move through that funny word, which we haven't really seen yet, umpalong. I have to do an umpalong. One of those carbons must become negative. Do I know a way to make one of those carbons negative? Yes. Yes, I do. What would that reagent be? We could add a Grignard reagent. If I add magnesium, what happens? I'd put the magnesium bromide there, which means I effectively have a negative carbon. That electron density could then go through and attack. I could do my ring, or not my ring expansion, but my carbon lengthening. Put my carbons on, and I'd have my tertiary alcohol after I followed that up with acid. Right? So a couple of steps. Everybody okay with that? What is the issue with this reagent? I have a Grignard reagent, which is a strong negative, and in that same structure I have a partial positive, which means the Grignard could attack itself. This kills its reactivity and doesn't allow me to react with the acetone structure. So how could I alter my starting compound so that I no longer have something that Grignard would react with? Well, turn it into an acetal. What happens when it's an acetal? Do I have an electrophilic site anymore? Nope. Now when I go through and do the Grignard, I can form that active Grignard reagent. That's an O. I can then react this with my acetone in step 1, followed by H+. I can make my alcohol. Okay, but what if I want that carbonyl still present? How do I get it back? Add water. add water and an acid, and I can reverse the reaction of the formation of the acetal, and I would end up with my final structure exactly the way I wanted it to be. So we can use the acetal as a way of protecting carbonyl functional groups. Okay. Neat little feature of them. Are there other ways we can build protecting groups? Yes, absolutely. We'll see them at the tail end of chapter 19, maybe. Any ideas why I throw in the maybe? We might run out of time. Why do we try to avoid protecting groups?
Adds extra steps.
It adds extra steps. What happens to your yield when you add extra steps? It goes down. Okay. So we would typically try to design a synthesis that prevents or negates the need to use a protecting group. Because as soon as I bring in a protecting group, I have to put it on and I have to take it off. That adds 2 steps to a synthesis that maybe didn't need it. That's 2 opportunities to lose yield. Even if I had a 99% success rate on both those steps, I'm now adding into the loss of my product. With 2 steps, not a big deal, but what if your synthesis has 50 steps? That's going to start to really eat into your yield. Not a good thing to do. Right? The extra added reasoning behind it, not just kind of from a financial standpoint, as we've mentioned it a couple times this semester. We'll use kind of a, well, we could use that. A little bit of a hint here. Green chemistry. Okay. If we're using a bunch of extra reagents, we're now using them to get rid of them. Okay. That's chemically wasteful. That's not green chemistry. Okay. So protecting groups aren't the greatest idea. They're slowly kind of getting phased out to a certain extent, okay, except that we need them as a tool. Okay. So every so often we'll end up using them. Nitriles. Nitriles are a polar pi bond, just like our carbonyls. We can go through and do the same kind of chemistry with them. We can react them with water. Okay. The water will go through and immediately form an amide. Okay. We're just breaking the pi bond and adding water across it. Okay. Notice that we don't end up exactly at an amide or after a single addition. So we added a single one in. What might we expect as a result? Probably expect something along those lines. Okay? Just added water across the pi bond. Why do we not end there? Why does it continue to go to the amide? Because nitrogen's not as what? Nitrogen does have lone pairs that could react. So under an acidic environment, okay, we could have those. You got me doing it now. It could pick up another hydrogen, which then means can polarize that pi bond, which then means that can shift in. So that nitrogen, being more basic than the oxygen, can pick up those hydrogens, okay? Eventually pushing us all the way to the amide. Why do we not see it, in theory, kick all the way off right away? Is it basic anymore? Officially not, because of resonance back through. We can continue to propagate that if we give it more time. Why? If it's not basic, it doesn't protonate. Why would it continue? Our favorite. Maybe 15 letters? 10 letters? It is an E. Equilibrium. Don't count it and prove me wrong. Okay. We're looking at an equilibrium. The presence of water, okay, as long as there's a high concentration of it, can force that reaction to go the other direction. Okay. The nitrogen and the water are in steep equilibrium with each other. They can go back and forth. We can do it under acidic conditions. We can also do it under basic conditions. We'll both end up at the exact same result eventually. Okay. Why is the textbook showing it in parentheses, though?
It's not the major product.
No. What eventually has to happen? from the amide, we have to have a nucleophile come and attack. Which bond would we break? Break the pi bond first, because the pi bond's our highest energy. Okay, then what do? We reform the pi bond and kick out a leaving group. So we would be doing a nucleophilic addition followed by a nucleophilic elimination, which is a mechanism we haven't talked about yet. That's why it's held in parentheses. Okay? It's not something you're officially responsible for. That's the next unit. Okay? So that's why they're trying to kind of hedge around that, but they're at least mentioning the fact that you still have to watch out for it. Okay? So our nitriles are irritating because we'll do nucleophilic additions like normal. We'll then do another nucleophilic addition followed by the nucleophilic elimination. The elimination part you aren't officially responsible for yet. Okay? There's the big long mechanism under acid hydrolysis. You can also do it under base hydrolysis, so there's our big mechanism for that. I'm not particularly concerned about those mechanisms, so I wouldn't stress on them. The next part of it is how can you get a nitrile? Okay. We can do this by reacting nitriles with carbonyls. So instead of doing a nucleophilic addition to a nitrile group, we can take the nitrile itself, or cyanide, and use it as a nucleophile with a carbonyl and do a nucleophilic addition directly. The result is we would end up with what is known as a cyanohydrin. Cyano because the CN, the hydrin because, whoops, or OH. Okay. Why is that functional group particularly useful, or why that structure particularly useful? At a single carbon, we have two big branches of reactivity coming out of it. So it's something that jumps out as a useful reagent because we can do a bunch of things from that one center, okay, just by exploiting it and reacting it with the nitrile. Okay. Other than that, that's about it. Okay. This reaction, though, is very, very slow. How could we speed it? Okay. And the part that we're referencing is the formation of it. That step is slow. Why is it slow? We want the nitrile to be what? A nucleophile. We want it to be CN minus. Is it currently CN minus? No. How could I speed this reaction up? Add a base, because HCN is an acid. So protonating would protonate this structure, and then at best it's going to keep the hydrogen on your HCN. You don't have that nucleophile. Okay. So the protonation step could be useful to activate the electrophile. The nucleophiles are a problem here. We need to get the nucleophile active.
If we added the acid and we get the alcohol, could that still react? Because you have a weak base, because you have electrons between the carbon and the nitrogen. So maybe you get a different structure than that.
You don't have enough of a nucleophile in the HCN to really get much. Okay. For the HCN to appropriately work, what's the very first step under the slow mechanism? You have to actually do the protonation anyway to form your nucleophile. Now that we have a nucleophile, we can react. If we add an acid outright, what happens? We may protonate the electrophile, but then we don't have the nucleophile. I missed that positive charge. Okay. Kind of, sort of. Okay. Oxygen versus nitrogen. I'll time you on this 30 seconds. Okay. So we're doing an atomic comparison. We're looking at our atom comparisons. As we do with all our reactions, we go back to our 5 primary things on determining a reactivity. We look at charge. Well, in this case, neither of them are charged. There's nothing to compare there. We move to the next thing, which is size. Is there a difference in size between nitrogen and oxygen?
No.
Within a row, there's very little change in size. Okay? So not enough to cause anything substantial. So there's no difference or no effect in size. So the next part is electronegativity. So yes, I listed size in the slides so that somebody might bite and say, oh, size is different. No, the size isn't particularly useful. We're really looking at the electronegativity. Okay? What do we get in the electronegativity? What is our difference? Oxygen is more electronegative than nitrogen. How is that going to affect the reactivity of each? Okay. And we could even narrow that down and say with regard specifically to carbonyls.
Nitrogen's going to be more reactive.
Nitrogen should be more reactive with a carbonyl than oxygen. Why?
Because it will hold electrons as well as the oxygen, so it'll give them up
How does our carbonyl react?
as an electrophile.
As an electrophile, which then means our nitrogen or our oxygen must act as the nucleophile. It must be willing to donate electrons. Okay? If oxygen is more electronegative, it is holding its electrons, preventing the donation. That means nitrogen is a better nucleophile than our oxygen. Why does that come into play? Well, when we're looking at reacting a carbonyl with, say, a nitrogen compound, let's just do NH3, one of our immediate or close to immediate intermediates would be something along these lines. Okay. We have the equivalent of what functional group that we talked about today? So hemiacetal is close, but there's no R groups. I would argue it's the hydrate, but it's that right vein. Okay. What did we say about the existence of either the hemiacetal or the acetal or the hydrates? They're not particularly stable, and it will quickly fall apart. How would we predict this particular structure to fall apart?
With the OH leaving.
With the OH likely leaving in this swap out. Okay. Yes, OH is a bad leaving group, so we would have to address the acidic or basic conditions under which this mechanism is occurring. And that's where this one gets even more irritating, because you're now looking at all sorts of positives and negatives floating through this, and trying to figure out the exact order to do your protonations and deprotonations is exceptionally challenging. Which is why I want you to go through and work out an explanation. So, groups 2 or 3, okay, or I'll accept it as 3 boards. Work out a mechanism to explain the following reaction. I want to see that reaction or that mechanism up on a whiteboard. A lot of negative charge. And if we go through and look at your mechanisms, you've got lots of positives and negatives showing up in pretty much every single one. Okay. The issue with that is that you need to make sure that the negatives you generate are not strong bases. Well, amide, NH2 minus, is a strong base. So at no point should you be generating a strong acid. Like, I don't know, water is a good leaving group. Okay. Or protonating the carbonyl. Okay. It is not an easy mechanism to work with. Okay. This is why when you go through and approach it, you should pick your conditions and stick to those conditions as best you can. And you will find, under some circumstances, that you're not going to have a choice, and you're going to have to come up with some other way to work around it. Okay, so I prefer to work under acidic conditions. I think it is easier for me to go through and see this one. So under acidic conditions, what should be the first step? Protonate the most basic site, which would likely be the nitrogen. Interesting. So we cancel the nucleophile by protonating. This is one of the reasons why we protonate as a catalyst. There's a relatively small concentration of the H+, meaning not all of the nitrogen has been occupied, meaning at some random opportunity in time, that happens to pick up a hydrogen from our solvent, which is likely going to be from our nitrogen, to cause our protonated state. This very quickly reacts with our nitrogen species to produce what is known as the tetrahedral intermediate. Why is it known as a tetrahedral intermediate? That carbon has 4 different things attached. Now what can happen? What's reactive about that structure? I would make the positive charge on the nitrogen my priority. So I would go through and deprotonate that. Okay, I'm still in an acidic environment. That acidic environment could donate a hydrogen to my structure. Oops, close enough. I have water as a good leaving group. That has a resonance contributor. I need something remotely basic, say like ammonia, still floating around in solution, to get me to my final product. Okay. Nitrogen is an SOB when it comes to reactions. If you're dealing with your carbonyls, what the nitrogen will effectively do is swap out the oxygen so that we can form what is known as the imine, I-M-I-N-E, the equivalent of a carbonyl. Okay. With that said, spend the rest of our time predicting what those potential products are. So I know that says a 10-minute timer, you get 3 minutes. Lucky you. See what you can come up with. We will pick up here on whatever Wednesday is, and then we'll be moving into our enolate chemistry, which is super exciting stuff. Lots of named reactions and kind of frustrating and irritating, but it's doing the same chemistry. We're taking a nucleophile, we attack the carbonyl, what things happen thereafter. I posted this weekend